Yes, what is Nernst equation? I'll just give you. E of m n plus bar m, it is E naught of m n plus bar m minus 2.303 RT by NF log m upon m n plus. Okay, so this is for this kind of an equation. Okay, now this is how you will write. It is the reduced form at the top, and the one which is getting reduced is at the bottom. M n plus, that is, this is there on the reactant side, m is there on the product side. So remember always it is product upon reactant, product upon reactant whenever you write Nernst equation. Now if it is for the whole after calculating, after solving for cathode minus anode, it is, you know very well that E cell is equal to E cathode minus E anode. So E cathode and E anode can be written like this for the zinc and copper electrochemical cell. Okay, so this is how you will write. This is for the equation Cu2 plus 2 electron giving you Cu, and this is for zinc 2 plus 2 electron giving you zinc. Okay, this is how you will write the equation. And then if you write the E cell will be E cathode minus E anode. So that is E of Cu2 plus bar Cu minus E of zinc 2 plus bar zinc. So if you replace all the expression, you will find that E naught cell, that is E naught of Cu2 plus bar Cu minus E naught of zinc 2 plus bar zinc. So this is your E naught cell. Okay, minus, so that 2.303 RT by NF will reduce to 0.059. Okay, upon 2. 2 is the number of electrons that is involved in the redox reaction, log zinc 2 plus upon Cu2 plus. Remember, zinc plus CuSO4 giving you zinc sulfate plus copper. Okay, I told you product upon reactant. Okay, product zinc sulfate is formed, so zinc 2 plus is there on the product side, CuSO4 is on the reactant side, so Cu2 plus is there in the bottom. Okay, so it is product upon reactant. So this is the basic equation, E naught cell minus 0.059 upon n is the number of electrons involved in that redox reaction, log of product upon reactant, and if at all there is any coefficient, then that coefficient will come in the form of power. Okay, say A or B. Okay, now this is your Nernst equation. Now let me talk about variation of molar conductivity with concentration, which is again a very important topic. Variation of molar conductivity with concentration. Okay, now here what you take molar conductivity along the y-axis and under root C, that is square root of concentration along the x-axis. Okay, now this has been studied for two different electrolytes, one a strong electrolyte like KCl and the other one a weak electrolyte like acetic acid. Okay, now look at the line when you study for a strong electrolyte for this KCl. Now here from left to right the concentration is increasing. So from right to left the concentration is decreasing. Okay, now you find that with decrease in concentration molar conductivity is increasing. Is it not? Here you are having KCl concentration and correspondingly the molar conductivity was somewhere here. Now as and when the concentration reduces, the molar conductivity has increased here. So there is only this much of difference, यहाँ से यहाँ तक, right? Now when you see acetic acid with decrease in concentration means dilution. Okay, so on dilution or decrease in concentration, how the molar conductivity is increasing steeply for acetic acid, you see. Okay, so remember, for a strong electrolyte the increase in molar conductivity is steep with increase in dilution or with decrease in concentration. But for a strong electrolyte like KCl, the increase in molar conductivity is marginal. Is that clear? तो यहाँ से to somewhere here, यहाँ से यहाँ तक increase हुआ, whereas acetic acid की case में यहाँ से यहाँ तक increase हुआ. Is that clear? So with increase in dilution for a weak electrolyte, the increase in molar conductivity is steep, whereas for a strong electrolyte, the increase in molar conductivity with increase in dilution is marginal. Okay, so this is what you have to be very clear. It's a very, very important topic. Now, between strong electrolyte and weak electrolyte, I have given you the differences, and I suppose all of you must be having the notes also. Molar conductivity increases with increase in dilution, both for weak electrolyte as well as for strong electrolyte. Molar conductivity increases with increase in dilution. This is common, but the increase in molar conductivity is marginal in the case of strong electrolyte, whereas in the case of weak electrolyte it is steep, right? Then on dilution, the distance between the ions increases. This you know very well. If you add water, what will happen? The distance between the ions, that will increase, but the number of ions per unit volume decreases. Okay, because of increase in distance, the ions, they independently contribute to molar conductivity, hence there is marginal increase. Okay, but in the case of weak electrolyte on dilution, it undergoes more dissociation as per Chatelier principle. Now this is an equilibrium expression. So what you know, when you add more and more of water, the equilibrium will shift in the forward direction. So more and more of ions will be formed. So number of ions per unit volume will increase, which will contribute to steep increase in molar conductivity. Is that clear? Now in the case of strong electrolyte, you can calculate molar conductivity at infinite dilution, that is molar conductivity at zero concentration, by extrapolating the line, because it was a straight line, it was linear. Okay, so you could extend it to cut the y-axis and you get the molar conductivity at infinite dilution. But since it was parabolic, it was moving in the form of a curve, so you cannot measure molar conductivity at infinite dilution for a weak electrolyte. Okay, so this is what is very important. You have to understand very clearly.